Hello everyone and welcome to this talk. I am Vaibhav from Indian Institute of Technology, Delhi, and today I will be presenting our paper Automatic Generation of Debug Headers through BlackBox Equivalence Checking accepted at CGO 2022. We start with these two informative charts demonstrating the growth in the compiler complexity. The first chart demonstrates the number of lines of code in the GCC compiler over time. Starting from 1992, the number of lines of code has increased linearly, basically as fast as humans could develop it. Today, GCC stands at over 18 million lines of code, which is an astounding amount of complexity. In the second chart, we see a similar growth in complexity for LLVM. It shows lines of code in LLVM's core components, mostly the include and lib directories in LLVM over time. Once again, we see a linear increase in complexity that is showing no signs of slowing down. The total lines of code of LLVM's core component stands at over 3 million LOC. So this gives us an idea of the modern compiler's complexity. Now let's see how it could impact the debuggability of the programs. Consider this example C program. Here x and y are defined as integer arrays of size n, and there's another integer variable named val. It contains a function s000, which has a local variable I initialized to 0. And there's a for loop from I equal to 0 to n that stores the addition of y of I and val into x of I in each loop iteration. Now, after we compile this C program with -o2 optimization flag, the corresponding abstracted assembly program generated is as shown here. Here's the beginning of the function s000. It stores the address of the first element of array x and the first element of array y into registers R1 and R2 respectively. It then stores the value of variable val into the register R3. After that, register R4 is assigned the result of addition of register R1's value with the number 4 times n. Why 4? Because we had compiled our program for a 32-bit machine and the size of an integer on this machine was 4 bytes. So R1 plus 4 times n means the address of the memory just after the last element in array x, and this is stored in the register R4. Next, the operation at A4 reads the contents of the memory pointed by register R2, adds R3 to it, and then stores the result back to the memory pointed by register R1. This is equivalent to the operation done at C3 by our C program. This is followed by the increments in the register values R1 and R2 by 4. This means both R1 and R2 now point to the next consecutive element of the arrays x and y respectively. Finally, register R1 is compared with R4, and if they are found to be equal, then the control flow is transferred to the instruction at A4 to perform the next iteration of the loop. Otherwise, the loop is finished and the function just returns. The register R1 is checked against register R4 to implement the comparison of variables I and n in the source code. Now let us observe a relation between the variable I, that is iteration number, and register R1 during each iteration of the source and the assembly program. When the value of variable I is 0, register R1 will point to the first element of the array x, that is x of 0. As variable I gets incremented to 1, R1 will point to the second element of array x, that is x of 1. When I will become 2, R1 will be pointing to x of 2, and so on. For example, when I will be n-1, R1 will point to x of n-1. Looking at this, we can say that R1 would be equal to x plus 4 times I. As we know, it's the job of a compiler to add the debugging information into an executable file, which then is consumed by a debugger such as GDB to allow programmers debug the program. So as a part of the debugging information, we would expect that the compiler would add this relation or mapping between source variable I in terms of register R1 into the executable. Let's check if that is the case when we debug this assembly program in a debugger, that is GDB. On the right hand side, there is a GDB debugging session for our compiler generated assembly program for this C source program. We set a breakpoint at function s000. When we run the program in GDB, we observe that the value of I is 0 initially, but even after we continue to the next iteration, we see a value of 0. This goes on for all the iterations of the for loop. This means that the compiler is unable to persist the relation of variable I in terms of registers in the assembly program. This is an annoying symptom of the overwhelming complexity of the compilers today, which we saw in the first few slides, and the deprioritization of the task of preserving the debugging headers by the compiler developers. And this is the problem we are trying to address. That is the problem of incomplete or incorrect debugging information for optimized assembly programs, but using a different technique. Let's first see a summary of our contributions and results. We present an algorithm and a tool that takes the original source code program and an existing equivalent optimized executable program generated by a compiler and automatically generate and update its debugging headers. Our tool is based on a BlackBox Equivalence checker, which is a standalone tool that takes two input programs and determines whether they produce equivalent observable behavior. We apply the black box equivalence checker to identify whether the optimized executable code is equivalent to the original source code. If the tool is able to determine that the two programs are equivalent, it generates a formal mathematical proof of equivalence. The proof is represented as a bisimulation relation that involves correlations between the program text segments across the two programs and relational invariants across the variables of the two programs at those intermediate correlated program points. The primary contribution of this paper is an algorithm based on linear algebra techniques that converts the relational predicates in the bisimulation proof into a set of mappings between the source code names and the machine names. These mappings are then added to the debugging headers of the executable file to improve its debuggability. The proposed algorithm also involves data flow analysis on the executable code to improve the debugging information further. We show significant improvements in the debugging headers of the executables generated by three different compilers, that is 73% for Clang or LLVM, 75% for GCC, and 12% for Intel C compiler. We demonstrate these improvements on programs taken from the test suite for vectorizing compilers, that is TSVC. Now, before going to the concrete problem statement and its solution, let's first have a look at some of the terminologies associated with our problem and solution. First, we start with a quick background on black box equivalence checking. As shown in the diagram, a black box equivalence checker is a standalone tool that takes two inputs, a source program and a machine code generated by a compiler. Without the knowledge of the individual transformations applied by the compiler, it checks for the functional equivalence of the two input programs. And if they are found to be equivalent, it outputs a formal mathematical proof consisting of two parts, one correlations and another invariants. As an example, let's consider the C source program and the assembly program we were looking at. If we pass these two programs as input to the equivalence checker, it will try to find the proof of equivalence and will output correlations as shown here. Let's try to understand these correlations. The first correlated PC pair is C0, A0, where the functions begin. When the transition from C0 to C2 happens in the source program, the corresponding transition from A0 to A4 happens in the assembly program. And they both reach to a state C2, A4. Similarly, when there is a transition from C2 to C3 to C2, in the source program, the corresponding transition A4 to A6 to A4 happens in the assembly program. These transitions in both the programs constitute a loop. This transition continues until the loop is finished and it stays in state C2, A4. Finally, when the loop ends, there is a transition from C2 to EC in the source program and the corresponding transition from A4 to A6 to EA in the assembly program. This puts both the programs in the last state, that is EC, EA. So in this correlation figure, each node represents a PC pair, while each edge represents running the instructions at those specified PCs. That is, edges represent the transfer functions. As a part of the equivalence proof, equivalence checker will also output the invariants present at each correlated PC pair. Let's look at the invariants inferred at one of the correlated PC pairs. The invariant produced at the correlated PC pair C2, A4 are as shown in the table. That is, x plus 4i equal to R1, y plus 4i equal to R2, val equal to R3, and x plus 4n equal to R4. Now that we saw an overview of black box equivalence checker, let's move to a quick background on debugging headers. As we know, a compiler translates a source program to an assembly program, and a debugger such as GDB uses this information embedded inside an assembly program to let us debug the program. To keep these two different tools interoperable, there needs to be a standard for such debugging information, and dwarf is one such popular standard for the debugging information format in ELF executable files. Note that ELF is a standard for an executable and linkable file format. So a compiler adds the dwarf debugging information inside the executable, and the debugger consumes this information. Mainly, there are three parts or sections inside the dwarf debugging information. The most important part or section of the dwarf debugging information is .debug_info section. This section consists of the program's nouns such as variable, types, etc. in the form of entries that are called debugging information entries or DIs. One such DI is shown here. Its tag base type represents an integer data type in our example C program. It specifies that the integer is signed with use of the dwarf attribute named encoding. The dwarf attribute byte size specifies that the integer size is 4 bytes. On the right hand side, here's another DI with its tag subprogram, and it represents the function S000 in our C program. It has attributes like name, declaration file, declaration line, declaration column to describe the function name and its declaration position in the source program. It has another attribute called type, which references the base type DI on the left side. By referring to the base type DI, it represents the return type for this function S000, which is int. The subprogram DI also has two more attributes, low PC and high PC, which denote the lowest and the highest PC in the function S000. Together, they represent the range of PCs belonging to this function S000. The third DI for our program is of type lexical block, which is a standalone DI with attributes low PC and high PC to describe a static scope of a block in the source program. The last DI in our program is of type variable, which represents the local variable I in our program. The DI mentions the position of the variable declaration along with its type, specified through a reference to an already existing base type DI shown on the left hand side. Note that the numbers 1, 2, and 3 present at the leftmost side denote the hierarchy of DIs. So the DI base type and subprogram are at the same level 1, while the DI lexical block is present inside the subprogram DI, and the variable DI is in turn a child of the lexical block DI. This is analogous to the hierarchical code structure present in our C source programs. There is one more dwarf attribute that we didn't yet look at. It's the location attribute that is part of the variable DI. The location attribute is referring to an offset 0x0 inside another dwarf section named .debug_location. The .debug_location section has a location list which specifies the value of variable I over the PC range 0xd to 0x25 in the form of a dwarf expression. The dwarf expression here specifies that the value is a literal 0. Now let's proceed to discuss our concrete problem statement. As we have seen through an example debugging session, in presence of rigorous optimizations, a compiler is often not able to persist the relation between the source variables and the registers in an optimized assembly program. And sometimes, even if it is present, it could be incorrect. So we define our problem to identify these missing or incorrect mappings between source variables and the assembly registers at each possible PC. And we do this through a different technique. We assume that an equivalence proof is already available as a bisimulation relation, that is a set of path correlations and invariants at the correlated PCs. We obtain the equivalence proof by passing the source C program and its corresponding optimized assembly program as input to the BlackBox equivalence checker. After finding the mappings, our aim is to use this information to automatically generate the debug headers. The problem of identifying the mappings can be divided into two subproblems. The first subproblem is to get the assembly expressions for the source variables. And the second subproblem is to identify the PC ranges where those assembly expressions hold. Let's now understand the first subproblem with an example. Consider this example C program. It has three integer arrays a, b, and aa as highlighted here. It defines a function foo and has a local pointer variable idx initialized to the address of array a. It has two nested loops with the outer loop ranging from I equal to 0 to n, with a local variable sum initialized to the value pointed by the pointer idx during each iteration. Then there's this inner for loop ranging from j equal to 0 to n. The inner for loop performs two computations. The variable sum is used to accumulate the product of the two elements in array AA and B. It then reassigns this sum to the location pointed to by the pointer idx. Let's consider the invariants generated by the equivalence checker at one of the correlated PC pairs for our source program and its generated optimized assembly program as shown in the table here. They relate the source variables I, J, and idx with the registers R1 and R2. We call these freestyle affine expressions and have the form as shown here in this mathematical equation, where Ci's are constant coefficients and Xi's are variables or registers from the source and the assembly program. We wish to convert these expressions into a form as shown here in the second mathematical equation. We call this form source to assembly affine expressions, where SI's represent source variables, CJ's represent coefficients, and AJ's represent assembly variables or registers. In this case, the source variables are I, J, and IDX, while the assembly variables are R1 and R2. Here we assume that A, B, and A are assumed to be constants and not variables because they represent the global variables or addresses that remain constant throughout the execution of the program. So our expected source to assembly affine expression should be as shown in the second table here. For example, I equal to R2 minus B divided by 4. We now describe a linear algebra technique that we use to arrive at such source to assembly expressions from the given freestyle expressions by the equivalence checker. We first convert the given freestyle expressions to a matrix form Ax equal to O as shown here in this slide. Matrix A represents the coefficients while the matrix X represents all the variables present inside the freestyle expressions. We next reorder the rows of the variable matrix X such that all the source variables come to the top while all the assembly variables or registers go after them. To keep the matrix equation consistent, we also need to reorder the corresponding columns in the coefficient matrix A. The matrix equation Ax equal to O after this reordering is shown here. Note that this ordering is an important part of our algorithm that we use in our claims specified later. Now, after this, we perform a set of matrix operations to convert this to a row reduced echelon form, that is RREF. The resulting matrix equation is as shown here. Now we traverse the coefficient matrix bottom to top and get the values of source variables in terms of the assembly variables or registers. Here we claim that due to our ordering of the variables and the properties of row reduced echelon form matrix, these resulting equations which we got after traversing this coefficient matrix from bottom to top directly represent the values of the source variables in terms of the assembly counterparts. Now that we have seen the first subproblem and its solution approach, we move forward to the second subproblem. Notice that the mappings we found so far are present only at the correlated PC pairs generated by the equivalence checker. And the equivalence checker would typically minimize the number of correlated points to simplify the proof generation process, and thus would typically correlate only the loop heads in the program. But as our goal is to fill in or fix the missing or incorrect mappings of source variables inside the debugging information, we need to find the mappings over the whole range of PCs in the program where they will be valid. So this is our next subproblem, that is to identify the maximal set of assembly PC locations where the variable correlations or mapping we found so far hold. Let's understand this problem at a high level with an example. Consider that there is an optimized assembly program with n instructions as shown here. Suppose the equivalence checker specified a predicate at the instruction 2. Now let's see how we try to propagate this predicate through the assembly program. Consider that the predicate source equal to register divided by 4 is coming from an instruction, and we want to see if we can propagate that through the next instruction. First case, or case A, is when the next instruction modifies a register that is present in our incoming predicate. In this case, because the register is getting modified, our original predicate would no longer hold true, and hence we would kill the predicate and it will stop propagating further. For case B, that is when the next instruction doesn't modify a register present in our incoming predicate, we would just propagate the predicate through the next instruction until we come across case A we saw in the last slide. But as you can imagine, due to directly killing the predicates in case A, this would limit our predicates to a relatively smaller range of PCs. So we try to improve case A by exploiting the reversible computation present in an assembly expression as shown in the next slide. Here, we first identify whether the computation of an instruction is reversible, for example, addition, subtraction, etc. If that is true, then instead of killing the predicate, we will modify it and propagate further. For example, consider that there is an instruction that performs register plus equal to 16. It clearly modifies the register present in our incoming predicate. So instead of killing the predicate, we modify it by replacing register with register minus 16 to keep it consistent with the modified register value. Thus, now we could propagate this new predicate further through the succeeding assembly instructions. We perform the predicate spreading in the forward as well as in the backward direction through the program to maximize the PCs where predicate could propagate. We implement this predicate spreading using data flow analysis, the details of which are specified in the paper. So this is how we get the updated executable that we can now run in the debugger to see the improvements in the debugging information. For the example program that we have seen, we will get the value of variable I correctly in terms of the register R1 instead of the constant 0 present before. So this is the overall workflow for our tool. We first pass the source code and the optimized machine code to the equivalence checker and use its output, that is the correlations and invariants, to perform some linear algebra techniques over it. That gives us the mappings of source variables in terms of the assembly counterparts. And finally, we perform data flow analysis to spread these predicates to as much assembly PCs as possible. And at the end, update the executable with the new debugging information. The compilers we used for our evaluation are GCC 8.4, Clang 12, and ICC 2021.2.0. The optimization flags used were -O3 with SSC 4.2. We performed our experiments on the TSVC benchmarks, which is the test suite for vectorizing compilers. To evaluate our improvements in the debugging information, we used two metrics. First being the number of instances or PCs where the debugging information was missing. By missing, we mean absent in the original but present in the updated object file. And second metric as the number of instances or PCs where the debugging info was incorrectly constant. That is constant in the original object file, but non-constant, that is having some register or memory location as part of it in the updated object file. Instead of doing it manually, we used an automatic evaluator to generate these metrics. And the results generated using this automatic evaluator are as shown here. The average percentage of PCs where at least one variable's missing debugging information was added is 18 for Clang, 73 for GCC, and 12 for ICC, while the percentage of PCs where incorrectly constant debugging info was corrected were found to be 55 for Clang, 2 for GCC, and 0 for ICC. We find that among all the three compilers, Clang was the one with most of its debugging info classified as incorrectly constant, while the GCC had most of its debugging info under the missing category. We find that the ICC had the least debugging info issues, be it the missing or the incorrectly constant category. Thank you.